Namaskar, I am Dan Gaude, Assistant Professor in Mathematics, Center for Distance Education, Shivaji University, Kolhapur. Today I will discuss last topic of classical mechanics, the kinematics of rigid body. Rigid body. In this chapter, we define a rigid body and describe how the numbers of degrees of freedom of a rigid body with n particle is determined. These are two types of motion involved in the case of rigid body, that is the translation and the rotations. Various set of variables have been used to describe the orientations of the rigid body. We will discuss in this chapter how the Eulerian angles and the complex Kelvin parameters can be used for the descriptions of the rigid body with one point fixed. Geometrically, matrix represents rotations. We will find the matrix of transformations in terms of the Eulerian angle and Kelvin parameter and establish the relation between them. This unit is devoted to the study of orthogonal transformation and its properties. First, rigid body. A rigid body is regarded as a system of many, at least three, non-collinear particles whose position relative to one another remains fixed. That is, distance between any two of them remains constant throughout the motion. The internal force holding the particle at fixed distance from one another are known as the forces of the constraint. These forces of constraint obey the Newton's third law of motion. First example, explain how the generalized coordinate of a rigid body with n particle reduces to 6 for its description. Generalized momentum, generalized coordinate of the rigid body. A system of n particles free from constraint can have 3n degrees of freedom and hence 3n generalized coordinate, but the constraint involved in the rigid body with n particle has holonomic and scalonomic and are given by Rij bar is equal to Aij, I is not equal to j, where Rij bar denotes the distance between the ith and jth particle and Aij are the constant. Equation 1 is symmetric in I and J, and I is not equal to J, as the distance of the ith from itself is 0. Therefore, the possible number of constraints is nc2 is equal to n into n minus 1 divided by 2. We notice that for n greater than 7, n into n minus 1 divided by 2 greater than 3n. Therefore, the actual number of degrees of freedom cannot be obtained simply by subtracting the number of constraints from 3n. This is simply because all constraints in equation 1 are not independent. To show the generalized coordinate of a rigid body with n particle reduced to 6 for its description, let a rigid body be regarded as a system of at least 3 non-collinear particles whose position relative to one another remains fixed. Thus, a system of 3 particles free from constraint has 9 degrees of freedom, but there involve 3 constraints. Hence, the number of generalized coordinates reduced to 6. Thus, the total number of degrees of freedom for 3 non-collinear particles A and B and C of a rigid body is equal to 6. This is because each particle has 3 degrees of freedom and lays 3 equations of the constraint. The position of each further particle, say P, requires 3 more coordinates for its description, but there will be 3 equations of constraint for this particle because the distance of P from A, B, C is fixed. Those 3 coordinates are for P and lays 3 equations of constraint for P gives 0 degrees of freedom. Thus, any other particle apart from ABC taken to specify the configuration of the rigid body will not add any degrees of freedom. Once the positions of the 3 of the particle of the rigid body are determined, the constant fix up the position of all remaining particles. Thus, the configurations of the rigid body would be completely specified by only 3 particles, 6 degrees of freedom, no matter how many particles it may contain. Next, describe the motions of the rigid body. A rigid body can have 2 types of motion. a translation motion and a rotational motion. Thus, a rigid body in motion can be completely pacified if its position and orientation are known. However, if one of the points of the rigid body is fixed, the translation motion of the rigid body is absent and the body rotates about any line through the fixed point. Again, if we fix up a second point, then the motions of the body is restricted to rotate the body non-collinear with other two. The position of the body is fixed and there is no motions of any kind. The coordinates of the third point alone will be able to locate the rigid body completely in space. It follows that the position of the rigid body is determined by any three non-collinear points of it. This is by 6 degrees of freedom of the 6 generalized coordinate. 3 coordinates are used to describe translation motion and other 3 coordinates are used to describe rotational motion. Since a rigid body with one point fixed has no translation motion and hence it has 3 degrees of freedom and 3 generalized coordinates which are used to describe the rotational motion.